What would it take to know that life exists beyond Earth? Not speculation, not belief, but evidence strong enough to withstand scrutiny. Would it be a planet that holds liquid water under alien skies? An atmosphere that refuses to settle into chemical equilibrium? Or a distant world whose air contains molecules that, on Earth, are produced only by living systems? And if such a world were found, how certain would we need to be before we allowed ourselves to say that something fundamental had changed? 120 light-years from Earth, orbiting a small red dwarf star, there is a planet that has forced scientists to confront these questions directly. Not because life has been confirmed there, but because the data gathered so far does not fit comfortably within what was once expected. The planet is known as K2-18b. Using the James Webb Space Telescope, astronomers have begun to analyze the light passing through its atmosphere as it moves in front of its star. That light carries information, subtle patterns shaped by molecules suspended in alien air. Water vapor has been detected. Carbon-bearing compounds have been identified. And among them, a molecule that on Earth is closely associated with biological activity. None of this proves that life exists on this world. But together, these signals raise a more difficult question. At what point does chemistry stop looking passive and start looking organized? The measurements themselves are robust. The interpretations are careful. Statistical confidence describes the reliability of the signal, not the certainty of its cause. Yet the implications are significant enough that K2-18b has become one of the most closely studied exoplanets ever observed. Not because it offers an answer, but because it sits at the boundary between what we understand and what we are only beginning to measure. This is not the story of a discovery declared. It is the story of how the search for life has entered a new phase. As K2-18b passes in front of its star, the event lasts only a few hours. During that brief window, the James Webb Space Telescope collects infrared light with extraordinary sensitivity. This light is not used to form a picture of the planet itself. Instead, it is broken apart into a spectrum, a precise measurement of how different wavelengths are absorbed as they pass through the planet's atmosphere. Each molecule absorbs light in its own way. Water vapor leaves one pattern, methane another, carbon dioxide another still. These patterns are not guessed at. They are measured in laboratories on Earth and catalogued with exacting detail. When Webb observes a distant planet, astronomers compare the incoming spectrum to those known molecular fingerprints. In the case of K2-18b, the analysis was especially challenging. The planet is small compared to its star, and the signal from its atmosphere is faint. The data must be combined across multiple transits and carefully corrected for noise, instrumental effects, and interference from the star itself. This is where interpretation begins. The spectrum showed features consistent with water vapor, methane, and carbon dioxide, molecules that had been hinted at before. But layered within those signals was a subtle absorption feature that did not immediately match the usual suspects. When researchers ran atmospheric models to explain it, one possible match emerged: dimethyl sulfide. On Earth, this molecule plays a quiet but important role. It is produced primarily by microorganisms in the oceans, released into the atmosphere, and broken down again over time. Its presence is tightly coupled to biological activity, not because it cannot exist without life in principle, but because on our planet, biology dominates its production. Detecting a signal consistent with dimethyl sulfide on another world does not mean the same process is occurring there. It means something is affecting the planet's atmospheric chemistry in a way that deserves careful scrutiny. The strength of the signal matters as much as its identity. The feature detected by Webb sits near the threshold of current observational limits. That means it cannot be taken at face value. Researchers must ask whether it could arise from overlapping signals, unknown chemical reactions, or limitations in the models themselves. This is why the result has been described not as a discovery, but as a confidence level. A statistical measure of how well one explanation fits the data compared to others. High enough to stand out, not high enough to settle the question. In astronomy, this is often where the most important work begins. K2-18b's atmosphere appears to be dominated by hydrogen, a gas that behaves very differently from the nitrogen and oxygen that make up most of Earth's air. Hydrogen-rich atmospheres can trap heat efficiently, smoothing out temperature differences and allowing planets far from their stars to remain warm. In some models, this creates conditions where liquid water could exist beneath thick atmospheric layers. These theoretical worlds are sometimes referred to as Hycean planets. The name combines hydrogen and ocean, reflecting the idea that such planets could host global seas beneath dense skies. They would not resemble Earth, but they might be chemically active in ways that support complex processes. If K2-18b fits this description, then its atmosphere and any underlying ocean would be closely linked. Gases produced or absorbed at the ocean's surface could accumulate in the atmosphere, altering its composition over time. In such a system, chemistry does not remain static. It evolves. That evolution is what scientists are trying to detect. One of the most intriguing aspects of the data is not any single molecule, but the overall balance between them. Certain combinations of gases are difficult to maintain together without a continuous source replenishing them. On Earth, life performs that role. It constantly pushes the atmosphere away from chemical equilibrium. Whether the same principle applies to K2-18b remains an open question. Methane, for example, is common in hydrogen-rich environments and can be produced through multiple pathways. Carbon dioxide is ubiquitous across planets and does not, on its own, imply anything biological. Water vapor can arise from many processes as well. None of these molecules are evidence of life by themselves. What draws attention is how they coexist. If future observations confirm that these gases persist together at stable levels, and if alternative explanations continue to fall short, then biological activity becomes one possible interpretation, among others. Not the only one, but one that can no longer be ignored. This is why K2-18b has become a focal point, not because it answers the question of life beyond Earth, but because it sharpens the question itself. For the first time, astronomers are not simply cataloging planets. They are testing ideas about how life might announce itself across interstellar distances. They are learning which chemical patterns are meaningful and which are misleading. The James Webb Space Telescope has not given us certainty. It has given us something more valuable, a way to ask better questions. For much of the past century, the search for life beyond Earth was guided by a simple assumption. If life exists elsewhere, it probably looks something like life here. That assumption shaped telescope designs, mission priorities, and even the language scientists used to describe habitability. Planets were judged by how closely they resembled Earth. Rocky surfaces, thin atmospheres, moderate temperatures, a narrow band around a star where liquid water might persist. K2-18b does not fit that picture. Its mass suggests a world several times heavier than Earth, with gravity strong enough to hold on to a thick atmosphere for billions of years. Instead of nitrogen and oxygen, that atmosphere appears to be dominated by hydrogen, the lightest and most abundant element in the universe. On Earth, hydrogen is rare in the atmosphere because our planet cannot retain it easily. On larger worlds, it can accumulate and persist. This difference alone changes almost everything. Hydrogen-rich atmospheres behave like powerful thermal blankets. They absorb and redistribute heat efficiently, smoothing temperature extremes between day and night, equator and pole. In some models, this allows planets orbiting relatively cool stars to maintain stable, warm conditions over vast areas, even if they are tidally locked, with one side permanently facing their star. In such environments, liquid water does not need to be confined to a narrow strip or a fleeting season. It could exist beneath the atmosphere across much of the planet, possibly in the form of a global ocean. This idea challenges a long-held assumption that habitable worlds must closely resemble Earth. Instead, it suggests that habitability may come in forms that are chemically and physically unfamiliar, yet potentially stable for far longer periods. Red dwarf stars like the one K2-18b orbits are smaller and cooler than the Sun, but they are also extraordinarily long-lived. While stars like our Sun burn for billions of years, red dwarfs can remain stable for trillions. If a planet can maintain an atmosphere and liquid water around such a star, it may have far more time for complex chemistry to develop. Time matters. On Earth, life appeared relatively quickly, but complex life took billions of years to emerge. A planet that remained stable for longer periods may allow processes to unfold that never had time to mature here. This is one reason K2-18b has attracted so much attention. Not because it mirrors Earth, but because it represents a different solution to the same fundamental problem: how to maintain energy, chemistry, and stability long enough for life to potentially arise. The concept of a Hysian world remains theoretical. No such planet has been confirmed directly, but the atmospheric signatures detected by Webb are consistent with what such a planet might produce: a hydrogen-rich envelope, water vapor, carbon-bearing molecules, and possibly, under certain conditions, chemical byproducts linked to biological processes. This does not mean that life exists there. It means that the range of environments considered worthy of serious investigation has expanded. Another reason scientists are cautious lies in the complexity of atmospheric chemistry itself. Molecules do not exist in isolation. They are created, destroyed, recycled, and transformed through countless reactions driven by heat, radiation, pressure, and time. Some combinations that appear biologically interesting can arise through processes that are not yet fully understood, especially under conditions unlike anything in our solar system. That uncertainty cuts both ways. It means some signals that look promising may turn out to have non-biological explanations. But it also means that some forms of life may leave signatures we do not yet recognize. The atmosphere of K2-18b is not being read as a message, but as a system, a dynamic environment shaped by physics and chemistry, and possibly by something more. One of the most important lessons emerging from this observation is methodological. Scientists are no longer asking a single question: is there life or not? Instead, they are asking a sequence of questions. What molecules are present? How stable are they? How do they interact? What processes could maintain them over time? Only when those questions are exhausted does biology enter the discussion. This layered approach reflects a shift in how the search for life is conducted. The goal is no longer to declare discovery, but to build confidence step by step, to rule out explanations patiently, to let the data constrain imagination rather than the other way around. Future observations of K2-18b will focus on exactly that. Additional transits, different wavelengths, independent analyses. Each new dataset will either strengthen or weaken the case that its atmosphere is being shaped by something beyond simple chemistry. This process will take time. In the meantime, the planet serves another purpose. It acts as a test case for the capabilities of the James Webb Space Telescope itself, a demonstration of how far atmospheric analysis has come and how much further it can go. Just a decade ago, detecting any molecule in the atmosphere of a planet more than 100 light-years away would have been considered extraordinary. Now, astronomers are debating subtle differences between overlapping chemical signals at the limits of instrumental precision. That change has happened quietly, without headlines, driven by improvements in sensitivity, stability, and data analysis. Webb does not see life. It sees patterns. And those patterns are becoming increasingly detailed. As more planets are studied this way, comparisons will become possible. One atmosphere will be set against another. Similar stars will host very different worlds. Some chemical combinations will prove common, others rare. It is within those differences that meaning may eventually emerge. K2-18b may turn out to be uninhabited, or it may represent a class of worlds where life is chemically subtle but widespread. Either outcome would reshape our understanding of habitability. For now, it occupies a narrow and fascinating space between certainty and speculation. A reminder that the universe does not need to resemble our expectations to remain deeply interesting. When scientists describe their confidence in a result, they are not making a statement about belief. They are describing how well a particular explanation fits the available data compared to alternatives. This distinction is subtle, but it is essential. In the case of K2-18b, the confidence figure attached to the dimethyl sulfide signal refers to the likelihood that the detected feature is real rather than a statistical fluctuation. It does not represent the probability that life exists on the planet. It measures how consistently a specific pattern appears across multiple observations and analytical models. Astronomers use statistical tools to evaluate this consistency. Each observation of a planetary transit adds a small amount of information. Individually, these measurements are noisy and incomplete. Combined, they can reveal trends that stand out from random variation. The stronger and more repeatable the trend, the higher the confidence that it reflects something physical rather than coincidence. Even so, high confidence in a signal does not automatically translate into a single explanation. A molecule detected in an atmosphere can arise through several pathways. Some are well understood. Others remain theoretical. In hydrogen-rich environments, chemistry behaves differently than it does on Earth. Reaction rates change. Stability thresholds shift. New pathways become possible. This is why scientists hesitate to label any single molecule as definitive evidence of life. Dimethyl sulfide is interesting because of its strong association with biology on Earth, not because it has been proven to be exclusive to life under all conditions. In unfamiliar environments, especially those dominated by hydrogen, it is still possible that non-biological processes could produce similar signals. Determining whether those processes are realistic requires further modeling and observation. This uncertainty is not a weakness of science. It is its boundary. The confidence figure attached to the signal simply marks the point at which it can no longer be dismissed as noise. It tells researchers that the feature is worth investigating further, not that the mystery has been solved. This distinction has been lost in many public discussions. Numbers carry weight. When people hear a percentage attached to a discovery, it feels conclusive. But in astronomy, percentages are tools, not verdicts. They guide where attention should be focused, not what conclusions should be drawn. K2-18b now sits at the center of that attention. As more data is collected, confidence levels can move in either direction. Signals can strengthen, weaken, or disappear entirely as models improve and assumptions are tested. This has happened many times before. Entire classes of exoplanets, once thought to be common, have been reclassified as detection techniques improved. The current debate surrounding K2-18b reflects a healthy process. One group of researchers proposes an interpretation. Others attempt to reproduce the result, challenge the assumptions, and explore alternative explanations. Over time, the picture becomes clearer, not through declarations, but through convergence. This process also highlights another important shift. Astronomers are no longer limited to discovering planets. They are beginning to compare them. As more hydrogen-rich worlds are studied, patterns will emerge. Some will show similar atmospheric compositions. Others will diverge in unexpected ways. If dimethyl sulfide or similar molecules appear repeatedly in certain environments and not in others, that pattern itself becomes meaningful. Context matters. A single planet can suggest a possibility. A population of planets can reveal a trend. This is why K2-18b is important, even if it ultimately proves lifeless. It serves as a reference point, a benchmark against which future observations can be measured. It forces scientists to refine their models and clarify what constitutes a meaningful biosignature. The James Webb Space Telescope was built to observe distant galaxies, the formation of stars, and the early history of the universe. Its role in the search for life is, in many ways, an unexpected extension of its capabilities. Yet it is precisely Webb's sensitivity to infrared light that makes this work possible. Infrared wavelengths carry information about heat and molecular vibrations. They allow astronomers to probe atmospheres that would be invisible at other wavelengths. Webb's instruments can detect minute changes in brightness, small enough to infer the presence of trace gases across interstellar distances. This precision is what enables debates like the one unfolding around K2-18b. Each additional transit observed refines the spectrum. Each refinement narrows the range of plausible explanations. Over time, uncertainty shrinks, not abruptly, but incrementally. This slow accumulation of evidence is not dramatic. It does not lend itself to sudden announcements. But it is how reliable knowledge is built. In parallel, researchers are developing new frameworks for interpreting atmospheric data. Rather than searching for single molecules, they're beginning to look for combinations of gases that persist together despite chemical instability. These states of imbalance can be more informative than any one compound alone. On Earth, life maintains such imbalance continuously. Oxygen and methane coexist in our atmosphere even though they should react and disappear. Their persistence is not accidental. It is sustained by biological activity. Whether similar imbalances exist on K2-18b remains uncertain. But the idea itself has changed how astronomers approach the problem. Instead of asking whether a planet looks like Earth, they ask whether its atmosphere behaves like a living system. That shift in perspective may prove to be one of the most significant outcomes of Webb's observations, regardless of what is ultimately concluded about this particular world. For now, K218b remains a question rather than an answer. A case study in how close modern astronomy has come to probing one of the oldest questions humanity has ever asked, and how careful it must be as it approaches the boundary between data and interpretation. As astronomers began to recognize how different K218b is from Earth, another realization followed close behind. If such a planet can exist, and if it can retain a stable atmosphere for billions of years, then it is unlikely to be unique. Surveys of nearby stars have already revealed that planets several times the mass of Earth are among the most common outcomes of planet formation. Worlds larger than Earth but smaller than Neptune appear frequently around red dwarf stars. Many were initially dismissed as inhospitable, assumed to be gas-dominated bodies without clear surfaces or stable environments. That assumption is now being revisited. Hydrogen-rich atmospheres were once considered a disadvantage. Too thick, too alien, too unlike Earth. But under the right conditions, hydrogen can act as a stabilizing influence rather than a disruptive one. It can trap heat efficiently, protect lower atmospheric layers from radiation, and smooth out extremes that would otherwise render a planet hostile. This means that the classical definition of a habitable zone, a narrow ring where Earth-like planets might support liquid water, may be too restrictive. For hydrogen-rich worlds, that zone could be much broader. A planet does not need to sit at a precise distance from its star to remain warm enough for liquid water. Atmospheric composition can compensate for orbital position, extending the range of potentially habitable environments far beyond what was once assumed. If that is correct, then the number of worlds worth investigating increases dramatically. Red dwarf stars make up the majority of stars in the galaxy. They are smaller, cooler, and longer-lived than stars like the Sun. Many host multiple planets. If even a fraction of those planets can maintain stable, hydrogen-rich atmospheres with underlying water reservoirs, then the diversity of potentially life-supporting worlds may be far greater than previously imagined. This does not mean that life is common. It means that the conditions under which life might arise are more varied. Webb's observations are beginning to provide the data needed to explore that variation. By comparing atmospheres across many planets, astronomers can begin to identify patterns. Some worlds may show signs of chemical equilibrium, where reactions have settled into stable configurations. Others may exhibit persistent imbalances that require continuous input of energy or material. Those differences matter. They allow scientists to separate planets shaped primarily by physics from those that may also be influenced by ongoing processes at or beneath their surfaces. Over time, a statistical picture emerges. Not a list of inhabited worlds, but a map of chemical behaviors across planetary environments. K218b occupies an early position on that map. It is close enough to be observed repeatedly. Its atmosphere is thick enough to produce detectable signals. Its star is quiet enough to allow stable measurements. Together, these factors make it an ideal laboratory for testing ideas that were once purely theoretical. But K218b is not the only target. Webb has already begun examining other planets orbiting red dwarf stars. Some are smaller, some hotter, some cooler. Each presents a different combination of mass, atmosphere, and stellar environment. As data accumulates, comparisons become possible. Do hydrogen-rich worlds commonly show water vapor? Do certain molecules appear together more often than expected? Are there atmospheres that resist explanation by known chemical processes? These are the questions now driving the field. They also highlight why caution remains essential. A single intriguing signal can inspire hypotheses. Multiple signals across many worlds are required to test them. Until that happens, individual planets remain suggestive rather than definitive. This cautious approach is not a retreat from discovery. It is an expansion of scope. Instead of asking whether one planet hosts life, astronomers are asking how planetary systems behave as a whole, how chemistry, energy, and time interact across environments that differ radically from Earth. The James Webb Space Telescope has made this shift possible not by answering the question of life, but by revealing how complex and varied planetary atmospheres truly are. In doing so, it has changed the search itself. The universe no longer appears as a collection of isolated planets awaiting classification. It looks more like a continuum of environments, each shaped by subtle balances between gravity, radiation, chemistry, and history. Some of those environments may be sterile. Others may be active. A few may support processes that resemble life as we know it. Others may support processes we have yet to recognize. K218b sits among these possibilities, not as a conclusion, but as a signal that the boundaries of habitability are wider than once believed, and that the tools to explore those boundaries are finally in place. One of the greatest challenges in the search for life beyond Earth is not detection, but interpretation. Nature is capable of producing complexity without intention, order without design, and chemistry that mimics biology under the right conditions. Astronomers are acutely aware of this. The history of planetary science is filled with signals that once seemed extraordinary, only to be explained later by unfamiliar physics or overlooked chemistry. Each apparent breakthrough has reinforced the same lesson. Caution is not hesitation. It is discipline. False positives are not mistakes. They are expected outcomes when exploring unfamiliar environments. A planet's atmosphere is shaped by countless variables. Stellar radiation breaks molecules apart. Gravity determines which gases are retained. Pressure alters reaction pathways. Time allows slow processes to accumulate visible effects. When these factors combine in ways that have no analog in our solar system, the resulting chemistry can appear strange, even suggestive. This is especially true for hydrogen-rich worlds. Hydrogen is highly reactive. It interacts readily with carbon, oxygen, sulfur, and nitrogen, creating a wide range of compounds. Under high pressure and constant radiation, some of these compounds can persist longer than they would on Earth. Others can form through reaction chains that do not occur naturally in oxygen-rich atmospheres. This means that molecules associated with life on Earth cannot be interpreted in isolation elsewhere. Dimethyl sulfide illustrates this problem clearly. Its importance lies not in what it proves, but in what it challenges. On Earth, biology dominates its production. In a hydrogen-dominated environment, the balance of possible sources is less certain. Determining whether non-biological pathways can realistically produce it requires extensive modeling and experimental validation. The same applies to methane. Methane is often described as a potential biosignature because of its biological role on Earth. Yet methane is also abundant throughout the universe, appearing in gas giants, icy moons, and interstellar clouds. Its presence becomes interesting only when considered alongside other gases, their relative abundances, and their persistence over time. This is why modern astrobiology focuses increasingly on systems rather than signals. A living world does not advertise itself through a single molecule. It alters its environment continuously. It drives chemical cycles away from equilibrium. It leaves fingerprints not in isolation, but in combination. Detecting such patterns remotely is extraordinarily difficult. Astronomers cannot sample these atmospheres directly. They cannot isolate layers, measure surface chemistry, or observe biological processes in action. They infer everything from light that has passed through a thin shell of gas and traveled across interstellar space. That light is then filtered through instruments, algorithms, and models, each introducing assumptions and uncertainties. Removing those layers without erasing the signal itself is one of the central challenges of the field. This is why independent confirmation matters. A signal observed once is interesting. A signal observed repeatedly by different instruments under different conditions becomes compelling. Over time, confidence builds not through a single measurement, but through convergence. K2-18b is now positioned at the beginning of that process. Future observations will attempt to detect the same features at different wavelengths. They will look for consistency across seasons, across stellar activity cycles, and across analytical methods. If a molecule persists under all of these tests, its origin becomes harder to dismiss. At the same time, laboratory experiments on Earth are attempting to recreate exotic atmospheric conditions. Chemists and physicists are exploring how molecules behave under pressures and compositions, unlike those found on our planet. These experiments help define what is plausible without life and what may require something more. This parallel effort is essential. Astronomy alone cannot answer the question of life. It must be combined with chemistry, physics, and planetary science. Each discipline constrains the others, narrowing the range of explanations until only the most robust remain. Even then, certainty may remain elusive. The search for life beyond Earth is not a problem that yields easily to yes or no answers. It is a gradient, a continuum of likelihoods shaped by incomplete information. Progress comes not from declarations, but from the slow elimination of alternatives. In this context, K2-18b represents a step forward, not a finish line. It demonstrates that we are now capable of identifying atmospheres complex enough to raise serious questions. That alone marks a turning point. For the first time, astronomers are not merely speculating about habitable environments. They are examining specific worlds in sufficient detail to test those ideas. This capability reshapes expectations. Future discoveries may not arrive as dramatic confirmations. They may appear as patterns that grow clearer with time. A molecule detected here. An imbalance noted there. A class of planets behaving in ways that defies simple explanation. Meaning will emerge gradually, across populations rather than individual cases. This shift requires patience, but it also offers resilience. Conclusions drawn from broad patterns are less vulnerable to reversal than those based on single observations. The James Webb Space Telescope was never intended to deliver a single moment of revelation. Its strength lies in accumulation. Each observation adds a small piece to a larger puzzle. K2-18b is one of those pieces. Not definitive on its own, but significant in what it suggests about what is now possible. To move from suggestion to confirmation, astronomers would need something far more demanding than a single compelling signal. They would need convergence. Multiple lines of evidence pointing in the same direction, each consistent with the others. each resistant to alternative explanations. In practical terms, this means detecting not just one molecule, but a network of chemical relationships that behave as a living system would be expected to behave. On Earth, life does not announce itself through isolated compounds. It reshapes the atmosphere continuously. Oxygen accumulates despite its reactivity. Methane persists despite its instability. Nitrous compounds cycle in and out of the air. Sulfur-bearing molecules appear and disappear in response to biological activity. Together, these processes create a dynamic imbalance that cannot be maintained by geology or chemistry alone. Reproducing that level of confidence for a distant planet is extraordinarily difficult. Webb can detect certain molecules with impressive sensitivity, but it cannot see everything. Some gases absorb light at wavelengths beyond its optimal range. Others exist in quantities too small to be detected across interstellar distances. Still others may be masked by overlapping signals that blur together in the spectrum. This means that even if life exists on K2-18b, its full chemical footprint may remain partially hidden. Confirmation would therefore rely on consistency rather than completeness. The same signals appearing repeatedly, their relative strengths remaining stable over time. Their presence correlating with what models predict for an active system rather than a static one. Time becomes a critical factor. If future observations show that certain molecules fluctuate in ways that correspond to changes in stellar radiation or orbital phase, that behavior itself becomes informative. On Earth, biological systems respond to environmental cycles. They grow, decline, and adapt. An atmosphere influenced by life is rarely static. Detecting such variation on another planet would be subtle, but powerful. It would also require patience. Webb's observation schedule is limited. Each transit observed must be carefully planned, calibrated, and analyzed. Competing scientific priorities determine where telescope time is allocated. No single planet can dominate indefinitely. As a result, building confidence will take years, not months. During that time, interpretations may change. Early conclusions may be refined or overturned as models improve and new data arrives. This is not a flaw. It is how scientific understanding advances. The temptation to declare certainty before this process unfolds is strong, especially when discoveries capture public imagination. But history offers a cautionary tale. Past claims of life on Mars, on Venus, and elsewhere have often faded under closer scrutiny. Those episodes did not weaken science. They strengthened it. Each false alarm clarified what evidence is required and how easily unfamiliar chemistry can mislead. The current generation of astronomers is acutely aware of that history, and it informs their caution. This context matters when interpreting the discussion around K2-18b. The excitement is real, but it is restrained. The language used in scientific literature remains careful. Claims are framed as possibilities, signals, and hypotheses, not conclusions. That restraint is intentional. It reflects an understanding that extraordinary claims demand extraordinary evidence, and that such evidence accumulates slowly. Beyond Webb, future instruments will play a crucial role. Next-generation space telescopes are being designed specifically to study exoplanet atmospheres. They aim to achieve higher contrast, finer spectral resolution, and greater stability. These improvements would allow scientists to separate overlapping signals more clearly and probe a wider range of molecules. Ground-based observatories will also contribute. Extremely large telescopes under construction on Earth will gather enormous amounts of light, enabling detailed follow-up studies of nearby planetary systems. Combined with space-based observations, they will provide complementary perspectives. Together, these tools will extend the reach of atmospheric analysis far beyond what is currently possible. Yet even with these advances, some uncertainty may remain. Life does not always advertise itself in ways that are easy to detect. Some biological systems may produce few atmospheric byproducts. Others may recycle gases internally, leaving little trace in the air. It is entirely possible that some inhabited worlds will appear chemically unremarkable from afar. Conversely, some lifeless worlds may appear deceptively complex. This ambiguity is not a failure of observation. It is a reflection of the diversity of planetary environments and the limitations imposed by distance. The search for life beyond Earth is therefore less like a single experiment and more like a long investigation. Clues accumulate. Hypotheses are tested. Confidence grows incrementally. K2-18b is one of the first planets where this process is unfolding in detail. It represents a transition from speculation to analysis, from imagination to measurement. Whether it ultimately proves to host life or not, it marks a point where the question itself becomes testable. That shift may prove to be its most lasting significance. Another quiet consequence of these observations is how they are reshaping ideas about planetary formation itself. For decades, planets were grouped into simple categories: rocky worlds close to their stars, gas giants farther out, ice giants beyond them. These categories were built from the architecture of our own solar system, because for a long time it was the only example available. Exoplanets have complicated that picture. K2-18b does not sit neatly in any traditional category. It is too large to be considered Earth-like, yet too small to resemble a gas giant like Jupiter. Its atmosphere appears thick, but not overwhelmingly so. Its composition suggests a world shaped as much by retained primordial gases as by later chemical evolution. This ambiguity is not accidental. It reflects the fact that planet formation is not a single pathway, but a spectrum of outcomes influenced by timing, environment, and chance. Around red dwarf stars, this diversity becomes especially pronounced. These stars form with large reservoirs of gas and dust, and their lower luminosity allows planets to accrete material differently than those orbiting Sun-like stars. Worlds that form early may retain hydrogen-rich envelopes. Others may lose them over time through stellar radiation and atmospheric escape. K2-18b appears to have retained its atmosphere. That retention has consequences. A thick atmosphere alters surface conditions, internal heat flow, and chemical cycling. It affects how energy is distributed and how long liquid water, if present, can persist. It also influences how a planet interacts with its star, buffering radiation and moderating extremes. In this sense, atmosphere and habitability are inseparable. The traditional search for life treated atmospheres as indicators, something to be read after a planet was found. Webb's observations suggest a different approach. Atmospheres are not just markers of habitability. They are active participants in shaping it. A planet's ability to hold onto an atmosphere may matter as much as its distance from its star. Its composition may matter as much as its size. Its chemical feedbacks may matter as much as its initial conditions. These ideas are still evolving. What Webb has provided is not a verdict, but a dataset rich enough to test them. Each new atmospheric spectrum adds a point of comparison. Each comparison refines models of how planets evolve over time. As these models improve, interpretations of worlds like K2-18b will sharpen. Some scenarios will be ruled out. Others will gain support. The range of plausible environments for life will become clearer, even if the presence of life itself remains unconfirmed. This shift toward population-level understanding marks a maturation of exoplanet science. Early discoveries focused on proving that planets existed beyond our solar system. The next phase involved cataloging them. Now, the emphasis is turning toward understanding how they behave as systems. K2-18b occupies a transitional role in that progression. It is not remarkable because it is unique, but because it is observable in detail. Its atmosphere is thick enough to leave detectable imprints. Its star is stable enough to allow repeated study. Its orbital geometry favors transit observations. These factors make it a reference point. Future discoveries may reveal worlds that are more Earth-like, more massive, or more exotic, but they will be interpreted in light of what has been learned here. This is why the conversation surrounding K2-18b continues to evolve. Each new paper does not replace the previous one. It adds context. It narrows uncertainty. It reframes expectations. In that sense, the planet has already served a purpose beyond any single claim. It has forced astronomers to confront the complexity of interpreting atmospheres that do not resemble Earth's. It has highlighted the limits of current instruments while revealing their potential. It has demonstrated that the search for life is not a matter of detection alone, but of interpretation, patience, and restraint. As more data accumulates, attention will inevitably shift. New targets will emerge. New signals will capture interest. But the lessons learned here will persist. The universe does not present its secrets cleanly. It reveals them gradually, through patterns that become visible only when enough pieces are assembled. K2-18b is one of those pieces. Not a conclusion, but a calibration. A reminder that the search for life beyond Earth is no longer a philosophical exercise. It is an observational science, constrained by data, guided by models, and tempered by uncertainty. And that uncertainty, far from diminishing the discovery, is what gives it meaning. Much of the attention surrounding K2-18b comes from the type of star it orbits. Red dwarf stars are the most common stars in the galaxy, making up the majority of stellar systems in our cosmic neighborhood. They are smaller and cooler than the Sun, but they are also remarkably long-lived. Where stars like the Sun burn steadily for billions of years, red dwarfs can remain active for trillions. This longevity changes the timeline of planetary evolution. Worlds orbiting these stars are not rushed by stellar aging. They exist in environments that can remain relatively stable far longer than Earth ever will. From one perspective, this is ideal. Life, at least on Earth, took immense amounts of time to develop complexity. Simple organisms appeared early, but multicellular life required billions of years of environmental stability. A planet with access to energy and chemistry over longer timescales may allow processes to unfold that never had time to mature here. From another perspective, red dwarf systems introduce challenges. Young red dwarfs are often active. They produce flares, bursts of radiation, and streams of charged particles that can strip atmospheres from nearby planets. Many planets in these systems orbit close to their stars, increasing exposure to this activity. Over time, some worlds lose their atmospheres entirely. K2-18b appears to have avoided that fate. Its mass and gravity likely play a role. A larger planet can hold onto its atmosphere more effectively, resisting erosion from stellar winds. A thick, hydrogen-rich envelope may also act as a protective shield, absorbing high-energy radiation before it reaches deeper layers. This combination of factors makes some red dwarf planets more resilient than previously assumed. It also complicates interpretation. A planet that retains a thick atmosphere may preserve chemical signatures for long periods, even if those signatures were produced under conditions that no longer exist. Chemistry can linger. Signals can persist long after the processes that created them have changed. This raises an important question. When we observe an atmosphere today, are we seeing an active system or a fossil record of past conditions? Answering that question remotely is difficult. It requires understanding not just what molecules are present, but how quickly they are produced and destroyed. It requires models that account for stellar activity, atmospheric escape, and internal planetary processes. In red dwarf systems, these factors interact in complex ways. Tidally locked planets, which always present the same face to their star, experience extreme contrasts between their day and night sides. Without a thick atmosphere, heat would not redistribute efficiently, creating harsh environments. With one, circulation can smooth those differences, creating surprisingly stable conditions. This again highlights the role of atmospheres as active regulators rather than passive layers. K2-18b may be an example of this effect. Its atmosphere appears capable of redistributing energy, moderating extremes, and sustaining chemical cycles over long periods. Whether those cycles include biological processes remains uncertain, but the physical framework exists. The prevalence of red dwarf stars means that worlds like this may be common. If even a small fraction of them retain thick atmospheres and underlying water reservoirs, the number of planets worthy of investigation grows significantly, not because they resemble Earth, but because they represent stable, long-lived environments. This reframes the search for life. Instead of focusing narrowly on Earth analogues, astronomers are now exploring a broader space of possibilities. Worlds that are warmer, heavier, richer in hydrogen, or shaped by different evolutionary histories. This does not dilute the search. It strengthens it. By expanding the range of environments considered plausible, science becomes more resilient to surprise. It becomes less dependent on assumptions drawn from a single example. At the same time, this expansion demands greater caution. The more diverse the environment studied, the easier it becomes to misinterpret unfamiliar chemistry. Signals that seem extraordinary in one context may be mundane in another. Understanding that context is essential. This is why K2-18b continues to occupy a central place in discussion. It sits at the intersection of several emerging ideas: hydrogen-rich atmospheres, long-lived red dwarf systems, complex atmospheric chemistry detectable across interstellar distances. Each of these ideas was once speculative. Together, they now form a testable framework. The planet itself may not provide the final answer, but it helps define the questions that follow. And those questions are shaping the next phase of exploration. Despite its extraordinary capabilities, the James Webb Space Telescope has limits. Those limits are not flaws. They are boundaries that define how conclusions must be drawn. Webb does not see surfaces. It does not peer beneath clouds or sample oceans. It does not detect organisms or biological structures. Everything it reveals about distant planets comes from light interacting with atmospheres. and atmospheres alone. This distinction matters. An atmosphere is not a complete record of a planet's interior, surface, or history. It is a dynamic interface between a world and its star, shaped by ongoing processes and past events. Some of those processes leave clear signatures. Others leave almost none. A planet could host life beneath an atmosphere that appears chemically unremarkable. Conversely, a planet could display complex atmospheric chemistry without hosting life at all. This ambiguity is unavoidable. Webb's instruments are tuned to specific infrared wavelengths. Molecules that absorb strongly in those bands are easier to detect. Others, even if present, may be effectively invisible. Some gases overlap in their absorption features, masking one another and complicating interpretation. Clouds add another layer of uncertainty. Thick cloud layers can flatten spectral features, hiding the chemical composition of deeper atmospheric layers. In hydrogen-rich worlds, clouds may form from compounds unfamiliar to Earth-based meteorology, further complicating models. K2-18b may be affected by this. If its atmosphere contains high-altitude clouds or hazes, they could obscure the lower layers where interactions with any underlying ocean would occur. Signals detected by Webb may therefore represent only part of the atmospheric system. This is why confirmation cannot rely on a single observational mode. Scientists attempt to work around these limits by observing planets across multiple wavelengths, using different instruments, and applying independent analytical techniques. Each approach reveals a slightly different aspect of the atmosphere. Where they overlap, confidence grows. Time also helps. Repeated observations allow astronomers to average out noise, identify persistent features, and detect subtle changes. Patterns that remain stable across years carry more weight than those seen only once. Yet even with patience and ingenuity, some questions may remain unanswered. Webb cannot directly detect surface pressure. It cannot determine ocean depth. It cannot distinguish between shallow seas and deep global oceans. It cannot tell whether chemistry is occurring at the surface, in the atmosphere, or deep below. These uncertainties place a ceiling on what can be claimed. This ceiling is why careful language matters, why interpretations are framed as scenarios rather than conclusions, why confidence levels are discussed separately from claims about life itself. Within these limits, Webb still represents a profound advance. It has moved the search for life from speculation to observation. It has provided real data from real planets, allowing hypotheses to be tested rather than imagined. It has revealed that planetary atmospheres are far more diverse than once assumed. K2-18b exemplifies this shift. Its atmosphere is not simply thick or thin. It is structured, dynamic, and chemically rich. That alone makes it valuable, regardless of whether life is present. The same is true for other planets now entering Webb's field of view. Some will show simple compositions. Others will display unexpected complexity. A few may resist explanation altogether. Each outcome refines understanding. Over time, a framework will emerge. Not a catalogue of inhabited worlds, but a classification of atmospheric behaviors. Some patterns will prove common, others rare. A few may correlate with planetary characteristics that suggest deeper processes at work. Life, if it leaves detectable traces, will likely emerge within that framework rather than as a singular event. This perspective changes expectations. Instead of waiting for a dramatic announcement, astronomers are building a cumulative picture. One planet at a time. One atmosphere at a time. each observation narrowing uncertainty, expanding context, and sharpening questions. K2-18b is an early example of this process in action. Its importance lies not in what it proves, but in what it demonstrates. That we now have the tools to interrogate distant worlds with sufficient precision to raise meaningful questions about habitability. That the search for life has entered a phase where restraint is not a lack of ambition, but a sign of maturity. As future telescopes come online, these limits will shift. Higher resolution instruments will separate overlapping signals more clearly. Broader wavelength coverage will reveal molecules currently hidden. Improved stability will allow subtler variations to be detected over time. Each advance will push the boundary of inference outward. But even then, interpretation will remain cautious. Because the universe does not yield its secrets easily, and because the cost of self-deception is high. The history of astronomy is a record of expanding horizons tempered by humility. Each generation sees farther than the last, and each discovers how much remains unknown. K2-18b sits within that tradition. Not as an answer, but as an invitation. An invitation to continue observing, questioning, and refining our understanding of what it means for a planet to be alive, active, or simply complex. As the limitations of current observations become clearer, another realization begins to take shape. The absence of certainty is not a failure of the method, but a reflection of how new this kind of inquiry truly is. For most of human history, planets beyond the solar system were hypothetical. Even a few decades ago, the idea of measuring the atmospheric composition of a world more than 100 light-years away would have sounded implausible. What Webb has done is not to answer the question of life, but to make it measurable in the first place. That shift from philosophy to instrumentation marks a fundamental change in how the problem is approached. The search for life has entered an era where evidence accumulates slowly, not dramatically. No single observation will carry the weight of confirmation. Instead, confidence will grow through repetition, comparison, and elimination. Patterns that appear consistently across different worlds will matter more than anomalies on any single planet. This is why K2-18b has drawn sustained attention. It is not because it stands alone, but because it offers a stable target that can be revisited, reanalyzed, and reinterpreted as tools and models improve. In this way, it functions less like a discovery and more like a calibration point, a reference against which future observations can be measured. As more planets are observed with similar techniques, astronomers will begin to see whether the chemistry detected on K2-18b is unusual or representative. If hydrogen-rich worlds frequently show comparable mixtures of water vapor, carbon-bearing molecules, and trace sulfur compounds, then the interpretation shifts. What once appeared exceptional becomes contextual. If, instead, such combinations remain rare, their significance grows. Either outcome is informative because it constrains how planetary atmospheres behave under different conditions and over long spans of time. This population-level perspective is essential. Individual planets can mislead. Entire classes of planets are harder to misinterpret. By building a statistical framework rather than chasing singular moments, astronomers reduce the risk of false conclusions while increasing the robustness of their insights. The question of life becomes embedded within a broader effort to understand planetary systems as dynamic, evolving entities shaped by physics, chemistry, and time. Time, in particular, plays a central role. A planet's present atmosphere is the result of its entire history. early formation conditions, stellar radiation, internal heat, atmospheric escape, and chemical cycling all leave imprints that persist long after the processes that created them have changed. When scientists observe an atmosphere today, they are seeing the cumulative outcome of billions of years of interaction. Disentangling which features are actively maintained and which are relics of the past is one of the most difficult challenges in exoplanet science. This difficulty is magnified in worlds unlike Earth. On our planet, decades of direct measurement and experimentation provide context. On K2-18b, everything must be inferred. Models must account for pressures and compositions never experienced in Earth laboratories. Reaction pathways must be extrapolated beyond familiar regimes. Each assumption introduces uncertainty, and each uncertainty must be acknowledged. Yet this uncertainty does not render the effort futile. It sharpens it. By forcing scientists to confront the limits of their knowledge, it drives the development of better models, more careful analyses, and more nuanced interpretations. It encourages collaboration across disciplines, bringing together astronomers, chemists, physicists, and planetary scientists to test ideas from multiple angles. In this environment, restraint becomes a strength. Claims are framed cautiously not because scientists lack confidence, but because they understand how easily unfamiliar systems can mislead. The history of planetary science is a record of confident assertions later revised or overturned as new data emerged. Each correction refined understanding. Each false lead clarified what evidence is required to move forward. K2-18b exists within this tradition. Its atmosphere has become a proving ground, not for claims about life, but for the methods used to detect and interpret potential biosignatures. It tests how well current instruments perform at the edge of sensitivity. It exposes where models succeed and where they fail. It reveals which assumptions hold and which require revision. As future observatories come online, the questions being asked will become more precise. Rather than asking whether a planet hosts life, scientists will ask how its atmosphere responds to energy, how quickly molecules are recycled, how stable chemical imbalances remain over time, and how these behaviors compare across different stellar environments. Life, if present, will be inferred not through a single indicator, but through a convergence of behaviors that resist explanation by non-biological processes. This approach reflects a broader shift in scientific thinking. Life is no longer treated as a binary condition, present or absent. It is treated as a process, something that interacts with its environment continuously. The challenge is not to spot life directly, but to recognize the signatures of that interaction across vast distances and limited data. The James Webb Space Telescope has made this shift unavoidable. By revealing the complexity of planetary atmospheres, it has shown that simplistic definitions of habitability are insufficient. Worlds once dismissed as unlikely candidates now demand serious attention. Others once considered promising may turn out to be chemically inert. The SOT space has expanded, and with it, the need for careful interpretation. K2-18b may or may not host life. That question remains open. What is no longer open is whether humanity has begun to develop the tools necessary to approach an answer. For the first time, observations are detailed enough to support sustained, evidence-based debate rather than speculation. That alone represents a milestone. As this process continues, the narrative will not resolve quickly. There will be revisions, disagreements, and periods of uncertainty. But beneath that surface complexity lies steady progress. Each observation refines understanding. Each analysis narrows the range of plausible explanations. Each comparison strengthens the framework within which life can be meaningfully discussed. In that sense, the importance of K2-18b does not depend on what is ultimately found there. Its value lies in what it has already changed. It has demonstrated that the search for life beyond Earth is no longer a question reserved for philosophy or imagination. It is an empirical endeavor, grounded in data, constrained by physics, and guided by caution. And that may be the most significant discovery of all. As this new phase of exploration unfolds, a subtle shift is occurring in how scientists talk about discovery itself. The language of sudden breakthroughs is giving way to the language of accumulation. Instead of searching for a single decisive observation, researchers are assembling bodies of evidence that grow stronger through consistency rather than spectacle. This is a quieter process, but a more durable one. It reflects an understanding that life, if it exists elsewhere, is unlikely to reveal itself in a single dramatic signal. It will emerge gradually, through patterns that become clear only after careful comparison across many worlds. K2-18b has become part of this broader transformation. It is not treated as an isolated anomaly, but as a case study that informs how future observations are designed and interpreted. Every uncertainty associated with its atmosphere has prompted new questions. How do hydrogen-rich envelopes evolve over time? How do clouds behave under pressures unlike those found on Earth? How stable are sulfur-bearing molecules when exposed to long-term stellar radiation? Each of these questions extends beyond a single planet and feeds into a growing framework for understanding planetary diversity. One of the most important lessons from this work is that habitability is not a static property. It is not something a planet either has or lacks forever. Instead, it is dynamic, shaped by feedback loops between atmosphere, surface, interior, and star. A planet may pass through habitable phases as conditions change. Oceans may appear and disappear. Atmospheres may thicken, thin, or transform entirely. Life, if it arises, must navigate these transitions, adapting or disappearing as environments evolve. This perspective complicates the search, but it also enriches it. It suggests that the universe may host worlds at many stages of potential biological development. Some may be chemically primed but lifeless. Others may host simple life without leaving strong atmospheric traces. A few may support complex systems that significantly alter their surroundings. Recognizing where a planet sits along this continuum requires patience and context, not haste. The emphasis on context has also changed how scientists think about biosignatures themselves. Rather than treating certain molecules as universal indicators, researchers increasingly emphasize conditional interpretation. A molecule's significance depends on where it appears, in what quantities, alongside which other compounds, and under what stellar conditions. Dimethyl sulfide, methane, water vapor, and carbon dioxide are not meaningful in isolation. Their meaning emerges only when their relationships are understood within a coherent atmospheric system. This systems-level thinking is one of the most important developments enabled by Webb. The telescope's sensitivity allows multiple molecules to be detected simultaneously, revealing interactions rather than isolated features. It is these interactions that hint at deeper processes, whether biological or not. Over time, as more planets are observed in similar detail, it will become possible to distinguish common atmospheric configurations from rare ones, and to identify which combinations resist explanation by known chemistry. The role of uncertainty in this process cannot be overstated. Far from undermining confidence, uncertainty defines the boundaries within which knowledge can grow. Each unresolved question becomes a target for further observation or experimentation. Each ambiguity motivates new models, laboratory studies, and theoretical work. In this way, uncertainty drives progress rather than halting it. K2-18b exemplifies this dynamic. Every claim about its atmosphere is provisional, subject to revision as new data arrives. Yet each revision refines understanding. The planet's atmosphere has already forced researchers to revisit assumptions about hydrogen-rich worlds, about the persistence of certain molecules, and about the range of environments that deserve close attention. These revisions ripple outward, influencing how other planets are evaluated. As future observations build on this foundation, the pace of discovery will likely accelerate, not because conclusions become easier, but because questions become sharper. With each new dataset, the range of plausible interpretations narrows. Patterns that once seemed ambiguous begin to stand out. Comparisons that were once impossible become routine. The search gains resolution, even if certainty remains elusive. It is also important to recognize that the search for life is not happening in isolation. It is embedded within a broader effort to understand planetary systems as products of cosmic evolution. Stars form, planets assemble, atmospheres evolve, and chemistry unfolds over immense spans of time. Life, if it appears, is one outcome of this process, not an external addition. Understanding life, therefore, requires understanding the systems that give rise to it. This perspective reframes the significance of discoveries like K2-18b. The planet is not valuable because it might host life, but because it reveals how planets behave under conditions unlike those found in our solar system. It expands the catalogue of known planetary states and challenges narrow definitions of what a world can be. In doing so, it enriches the context within which life can be meaningfully discussed. As the field continues to mature, expectations will adjust. The question will shift from whether life exists elsewhere to how often it emerges under different conditions and how it shapes the worlds it inhabits. These are deeper, more complex questions, and they demand careful, incremental answers. K2-18b is one step along that path. It does not resolve the mystery of life beyond Earth, but it brings that mystery into sharper focus. It shows that the tools now exist to probe distant worlds with unprecedented detail. It demonstrates that the universe is chemically rich and dynamically complex. And it reminds us that discovery is not always a moment of revelation, but a process of understanding that unfolds over time. In that sense, the story of K2-18b is not about what has been found, but about what has become possible. It marks a transition from wondering whether life might exist elsewhere to developing the methods required to find out. That transition, more than any single signal or molecule, represents a turning point in humanity's exploration of the cosmos. As this body of work expands, another quiet but important realization emerges. The search for life beyond Earth is no longer centered on finding confirmation that mirrors our own existence. It is becoming an effort to understand how complexity arises naturally in planetary systems, whether or not that complexity ever crosses the threshold into biology. This distinction matters because it reframes success. A planet does not need to host life to teach us something profound about the universe. It needs only to demonstrate how chemistry, energy, and time interact under unfamiliar conditions. K2-18b has already done that. Its atmosphere has revealed combinations of gases that challenge simple expectations, forcing scientists to reconsider which environments deserve careful attention. In doing so, it has weakened the assumption that Earth-like conditions are the only meaningful target. Instead, it suggests that habitability may be an emergent property of many different planetary configurations, some of which may appear counterintuitive when judged by terrestrial standards. This shift also alters how scientific caution is perceived. Caution is often mistaken for doubt, but in reality, it is a form of respect for complexity. When researchers resist definitive claims, they are acknowledging how many interacting variables remain unresolved. They are recognizing that planetary systems do not behave like controlled experiments, but like evolving networks shaped by history as much as by present conditions. Each atmosphere is the outcome of countless prior states, many of which are no longer directly observable. In this context, the demand for absolute certainty becomes unrealistic. What matters instead is convergence. Independent observations pointing toward the same interpretation. Models that remain stable as assumptions are varied. Laboratory experiments that reproduce key behaviors under simulated conditions. When these strands align, confidence grows naturally, without the need for declarations. The current discussion surrounding K2-18b reflects this process in motion. Some interpretations emphasize its potential as a Hycean world, one where a hydrogen-rich atmosphere could coexist with liquid water below. Others focus on the uncertainties introduced by clouds, photochemistry, or untested reaction pathways. Both perspectives contribute to progress because they sharpen the questions that future observations must address. Over time, this iterative refinement will lead to clearer distinctions. Some planets will reveal atmospheres that behave predictably, settling into chemical equilibrium dominated by known physical processes. Others may resist such explanations, maintaining persistent imbalances that demand additional sources of energy or material. It is within these resistant cases that the strongest candidates for biological influence may eventually be found. Even then, interpretation will remain probabilistic rather than absolute. Life does not leave a single universal signature. It expresses itself differently depending on environment, scale, and evolutionary history. Recognizing those expressions from afar requires flexibility, patience, and a willingness to revise assumptions as new data arrives. The James Webb Space Telescope has made this approach unavoidable. By revealing complexity where simplicity was expected, it has shown that the universe does not conform to neat categories. Planets exist along continua rather than in boxes. Atmospheres evolve rather than remain fixed. Habitability emerges from interaction rather than design. K2-18b is one example of this broader lesson. Its value lies not in confirming a hypothesis, but in expanding the space of plausible ones. It demonstrates that worlds unlike Earth can still exhibit rich dynamic chemistry, and that such chemistry can now be studied in detail across interstellar distances. As more planets are observed, patterns will become clearer. Some combinations of gases will prove common across many environments. Others will remain rare. Statistical analysis will replace anecdote. Confidence will be built not on individual cases, but on populations. In this way, the search for life will gradually align with the methods that have proven successful in other areas of science, where understanding emerges from comparison rather than singular events. This evolution in method also carries philosophical implications. It suggests that life may not be an anomaly, but a possibility embedded within the laws of physics and chemistry. Not guaranteed, not ubiquitous, but attainable under a range of conditions wider than once assumed. Whether that possibility is realized frequently or rarely remains unknown, but the framework for investigating it is now firmly in place. K2-18b sits at the threshold of that framework. It is close enough to study repeatedly, complex enough to challenge interpretation, and stable enough to serve as a long-term reference. Its atmosphere has already shaped the direction of inquiry, influencing how future targets are selected and how their data is analyzed. As observations continue, attention will shift naturally. New planets will take center stage. New signals will inspire debate. Yet the influence of K2-18b will persist, embedded in the methods and assumptions that guide those future investigations. In this sense, its importance transcends any single claim about life. It represents a moment when the search itself changed character, when speculation gave way to measurement, when imagination became constrained by data, when the question of life beyond Earth moved from philosophy into the realm of testable science. That transition is still unfolding. Its outcome remains uncertain, but its significance is already clear. For the first time, humanity is not merely asking whether life exists elsewhere in the universe. It is learning how to find out. As this understanding deepens, another layer of significance becomes apparent. The search for life beyond Earth is not only about distant planets, but about refining how humanity understands its own place in the universe. For centuries, Earth was assumed to be exceptional by default, not because evidence demanded it, but because no alternatives were known. Each new discovery has slowly eroded that assumption, replacing it with a more nuanced view in which Earth is one example among many possible outcomes of planetary evolution. K2-18b contributes to this shift not by proving anything extraordinary, but by demonstrating how easily complexity can arise under conditions very different from those that shaped our own world. What Webb has revealed is not a universe finely tuned to replicate Earth, but one capable of generating a wide variety of stable, chemically active environments. Some of these environments may never host life. Others may host life that leaves little trace. A few may support systems robust enough to alter entire atmospheres. The difficulty lies in distinguishing between these possibilities, using limited information carried across immense distances. That difficulty, however, is no longer theoretical. It is being confronted directly through observation and analysis. This confrontation has already changed how scientists think about future missions. Rather than designing telescopes solely to search for Earth analogs, planners are increasingly prioritizing flexibility. Instruments are being optimized to detect a wide range of molecules, to operate across broader wavelength ranges, and to achieve the stability required for long-term monitoring. The goal is not to confirm a single hypothesis, but to remain sensitive to outcomes that may challenge existing frameworks. In this evolving landscape, certainty becomes less important than adaptability. A discovery that contradicts expectations is not a setback. It is an opportunity to refine understanding. K2-18b exemplifies this principle. Its atmosphere does not fit neatly into prior categories, and that misalignment is precisely what makes it valuable. It forces models to stretch, assumptions to be tested, and definitions to be reconsidered. This process also underscores the importance of humility in scientific interpretation. The farther observations extend beyond familiar territory, the easier it becomes to project known patterns onto unknown systems. Avoiding that temptation requires constant vigilance. It requires separating what is observed from what is inferred, and what is inferred from what is imagined. The careful language used by researchers studying K2-18b reflects this awareness. It is not an attempt to diminish excitement, but to preserve accuracy. Over time, the accumulation of such carefully interpreted data will reshape expectations. The question will shift again, away from whether life exists elsewhere, and toward how often complex chemistry leads to biology under different circumstances. That question is more difficult, but also more informative. It acknowledges that life is not a binary outcome, but a process embedded within planetary evolution. In this sense, K2-18b represents a waypoint rather than a destination. It marks a moment when observational capability caught up with long-standing curiosity, when technology advanced far enough to transform speculation into structured inquiry, when the search for life became less about belief and more about method. As future observations build on this foundation, patterns will emerge that no single planet could reveal alone. Similar atmospheric behaviors may appear across unrelated systems. Certain chemical combinations may prove transient, others persistent. Some environments may consistently resist explanation without invoking additional processes. Each pattern will narrow uncertainty, even if it never eliminates it entirely. The universe, it seems, does not offer simple answers. Instead, it offers gradients, continua, and overlapping possibilities. Understanding those possibilities requires patience, rigor, and an acceptance that some questions may remain open for long periods of time. The presence or absence of life on K2-18b may be resolved years from now, or it may remain ambiguous indefinitely. Either outcome would be informative. What matters is that the process has begun. Humanity now possesses instruments capable of probing the atmospheres of distant worlds with enough sensitivity to ask meaningful questions. It can compare those worlds, test models against data, and refine its understanding incrementally. That capability did not exist before. In the long view, this may prove more transformative than any single discovery. The realization that life is a question that can be approached scientifically, even if it cannot yet be answered definitively, changes how the universe is perceived. It shifts the narrative from isolation to possibility, from uniqueness to diversity. K2-18b stands as an early example of this shift. Not because it confirms that life exists elsewhere, but because it demonstrates how close humanity has come to being able to tell the difference between chemistry alone and chemistry shaped by something more. The universe has not yet revealed its answer, but it has revealed enough to show that the question is no longer beyond reach. As the field advances, one final tension becomes increasingly clear. The tools humanity now possesses are powerful enough to reveal complexity, but not yet powerful enough to resolve every ambiguity that complexity creates. This tension defines the current moment in the search for life. We are no longer limited by imagination, but we are still constrained by distance, signal strength, and incomplete information. K2-18b sits precisely within that tension. It offers enough detail to provoke serious scientific debate, yet withholds enough clarity to prevent easy conclusions. That balance is not accidental. It reflects the natural boundary between observation and inference. What Webb has effectively done is expose the layered nature of planetary reality. Atmospheres are not static shells. They are the products of ongoing interaction between stellar radiation, planetary gravity, internal heat, and chemistry unfolding over immense spans of time. Some of those interactions are rapid, others slow. Some leave clear signatures. Others leave only subtle traces. When scientists observe an atmosphere today, they are seeing a snapshot of a process that may have been evolving for billions of years. Understanding that snapshot requires reconstructing a history that cannot be observed directly. This is why the language surrounding K218b remains careful. Every claim is provisional, not because evidence is weak, but because evidence is incomplete. The distinction matters. Incomplete evidence does not invalidate a hypothesis. It defines the work that remains to be done. Each uncertainty becomes a constraint, narrowing the space of plausible explanations rather than expanding it. Over time, this process transforms possibility into probability, and probability into understanding. The broader implication is that life, if it exists elsewhere, may not reveal itself in the way humanity once expected. Early visions of extraterrestrial life imagined obvious signals, dramatic changes, or unmistakable markers. What Webb suggests instead is subtlety. Life may announce itself quietly, through persistent chemical imbalances, through patterns that only become meaningful when compared across many worlds, or through behaviors that resist explanation by non-biological processes alone. Recognizing those signs requires patience and an acceptance that certainty will emerge gradually, if at all. This gradualism marks a profound cultural shift. The search for life is no longer framed as a race toward a singular discovery, but as an ongoing investigation into planetary behavior. Success is measured not by headlines, but by improved models, tighter constraints, and deeper understanding. In this framework, even a null result is valuable. Knowing that certain environments do not support biological activity is just as informative as knowing that others might. K218b contributes to this framework by expanding the range of environments considered worthy of attention. It challenges the assumption that life requires Earth-like conditions and invites consideration of worlds shaped by different balances of chemistry and physics. Whether or not life exists there, the planet has already reshaped the questions being asked. It has moved the discussion away from imitation and toward exploration. As future missions build on Webb's foundation, this shift will accelerate. New telescopes will observe planets at higher resolution, across broader wavelength ranges, and over longer periods of time. They will track changes rather than static states. They will compare atmospheres across populations rather than focusing narrowly on individual cases. With each advance, the distinction between chemistry and biology will become clearer, even if it never becomes absolute. In this evolving landscape, humility remains essential. The universe has a long history of defying expectations. Phenomena once thought rare have proven common. Others once assumed universal have turned out to be fragile or fleeting. The search for life will almost certainly follow a similar pattern. Some early assumptions will be revised. Some promising avenues will close. Others will open unexpectedly. K218b stands as a reminder of this uncertainty. It is neither a confirmation nor a refutation. It is a data point rich enough to matter, complex enough to challenge, and accessible enough to study in detail. Its true legacy may lie not in what it reveals about life, but in how it refines the methods used to search for it. In the end, the question of life beyond Earth may never yield a single definitive answer. It may instead resolve into a spectrum of outcomes, shaped by environment, history, and chance. Some worlds may host biology that transforms entire atmospheres. Others may harbor life quietly, leaving only faint traces. Many may remain lifeless despite favorable conditions. Understanding that spectrum is a scientific challenge unlike any humanity has faced before. What is certain is that the search has crossed a threshold. It is no longer speculative in nature. It is empirical, model-driven, and constrained by observation. K2-18b is one of the first planets to occupy this new territory, where data is sufficient to support sustained inquiry, but not yet sufficient to close debate. That territory will only expand. As instruments improve and observations accumulate, the universe will become less mysterious in some ways and more complex in others. The simplicity of being alone or not alone will give way to a richer understanding of how life fits within the broader context of cosmic evolution. That understanding will not arrive all at once. It will be assembled gradually, planet by planet, atmosphere by atmosphere. K2-18b is part of that assembly, not as an answer, but as evidence that the question itself has become something humanity can finally approach with rigor, patience, and care. As this investigation continues, one more implication quietly takes shape. The search for life beyond Earth is beginning to resemble other mature sciences, where understanding emerges not from singular moments of revelation, but from the gradual tightening of uncertainty. In such fields, progress is measured by how much remains unexplained, rather than by how quickly conclusions are reached. K2-18b exemplifies this transition. Its atmosphere has not delivered certainty, but it has reduced ignorance. It has narrowed the range of plausible explanations and forced refinement of ideas that once relied largely on speculation. This refinement is already influencing how future discoveries will be interpreted. Planets will no longer be evaluated solely on whether they appear promising at first glance. Instead, they will be placed within a broader comparative framework. How does this atmosphere behave relative to others around similar stars? How stable are its chemical features over time? Do certain combinations recur across different systems, or are they isolated cases? These questions mark a shift from discovery-driven excitement to pattern-driven understanding. Within that framework, the idea of a definitive biosignature begins to lose its simplicity. Life does not operate as a single chemical switch that can be flipped on or off. It is a network of processes that interact with their environment continuously. Some of those interactions may be subtle, others may be intermittent. Many may be masked by competing processes that operate on similar timescales. Recognizing life, therefore, becomes less about identifying one molecule and more about understanding how an entire system behaves over time. This perspective reframes the role of telescopes like Webb. Their purpose is not to deliver final answers, but to provide data rich enough to sustain this kind of systems-level inquiry. Webb's sensitivity allows scientists to observe atmospheres as dynamic entities rather than static compositions. That capability is transformative, even if it does not yet permit definitive claims about biology. K2-18b has already demonstrated the power of this approach. Its atmospheric signals have prompted debates that extend beyond the planet itself. They have forced reconsideration of how hydrogen-rich atmospheres evolve, how clouds and hazes influence interpretation, and how chemical pathways operate under unfamiliar conditions. Each debate sharpens the tools needed to evaluate future targets. As more planets are studied, it is likely that some will resemble K2-18b in broad outline, while others will differ in important ways. These differences will matter. They will help identify which features are generic outcomes of planetary physics and which may require additional explanations. Over time, this comparative process will allow scientists to distinguish between atmospheres shaped solely by non-biological processes and those that exhibit behaviors more difficult to account for without tamburo, invoking sustained chemical input. Even then, certainty may remain elusive. The universe is vast, and planetary environments are diverse. It is entirely possible that life exists in forms that leave minimal atmospheric footprints, or that life elsewhere operates on chemical principles unfamiliar to Earth-based biology. If so, detection will require methods and assumptions that have not yet been developed. This possibility does not undermine the current effort. It reinforces its importance. By exploring a wide range of planetary environments, scientists increase the chances of encountering unexpected behavior. Each surprise expands understanding, even if it complicates interpretation. In this context, patience becomes a defining virtue. The search for life is no longer a sprint toward a headline, but a long-term investigation that will unfold over decades. It will be shaped by technological advances, theoretical breakthroughs, and the steady accumulation of data. K218b is one of the first planets to be studied deeply enough to anchor this process. Its significance, therefore, lies not in what it confirms, but in what it enables. It shows that atmospheres can be analyzed with enough precision to raise meaningful questions. It demonstrates that planetary diversity is greater than once assumed. It proves that the search for life has moved beyond conjecture into disciplined inquiry. As future missions extend these capabilities, the boundary between chemistry and biology will become increasingly well-defined. Not because life announces itself clearly, but because non-biological explanations will be constrained more tightly. The space of uncertainty will shrink, even if it never disappears entirely. That shrinking space is where understanding lives. K218b occupies that space today. It stands at the edge of what current instruments can resolve, offering just enough information to challenge assumptions and just enough ambiguity to demand caution. It is neither a solution nor a distraction. It is a test case for a new way of studying planets. In the long view, this may be remembered as the moment when the search for life became methodical rather than speculative, when the question of whether life exists elsewhere ceased to be philosophical and became observational, when humanity began to build the tools, frameworks, and patience required to approach one of its oldest questions with scientific rigor. The answer, whatever it turns out to be, will not arrive suddenly. It will emerge slowly, through patterns recognized, alternatives eliminated, and confidence built over time. K218b is one step along that path, marking not the discovery of life, but the maturation of the search itself. As this search matures, it begins to echo patterns seen in other areas of science where complexity resisted early simplification. In those fields, progress did not come from discovering a single decisive signal, but from learning how to interpret many imperfect ones together. Climate science, evolutionary biology, and cosmology all followed similar paths. Each began with broad questions, moved through periods of overconfidence and correction, and eventually settled into frameworks that could accommodate uncertainty without collapsing under it. The search for life beyond Earth appears to be following the same trajectory. K218b occupies a place within that trajectory not because it answers the question, but because it exposes the difficulty of answering it well. Its atmosphere has become a proving ground for methods rather than a showcase for conclusions. Every attempt to interpret its chemistry reveals how much context matters, how easily assumptions can mislead, and how necessary it is to distinguish between what data shows and what it merely suggests. This discipline is not a barrier to discovery. It is the mechanism by which discovery becomes durable. One of the most important outcomes of this discipline is the gradual decoupling of excitement from certainty. A finding can be fascinating without being definitive. A signal can be important without being conclusive. This distinction allows the field to move forward without collapsing under the weight of its own expectations. It creates space for revision, debate, and refinement, all of which are essential when working at the limits of observation. In practical terms, this means that future announcements will likely feel less dramatic than many expect. They may arrive as updates rather than revelations, as refinements rather than breakthroughs. A molecule detected at one wavelength may later be constrained more tightly at another. A signal initially attributed to one process may be reassigned to another. Each adjustment will narrow uncertainty, even if it complicates the narrative. This process is already visible in how K2-18b is discussed within the scientific community. Language remains conditional. Interpretations are framed as scenarios. Alternative explanations are presented alongside preferred ones. This is not indecision. It is method. It reflects an understanding that planetary systems are not static targets, but evolving environments shaped by interactions that are only partially observable from afar. The broader implication is that life, if it exists elsewhere, may not conform to human expectations of clarity. It may not announce itself in unmistakable terms. Instead, it may reveal itself indirectly, through persistent deviations from chemical equilibrium, through atmospheric behaviors that resist explanation by known physical processes, or through long-term stability that suggests continuous regulation rather than passive decay. Recognizing such patterns requires more than instrumentation. It requires frameworks capable of integrating disparate lines of evidence. It requires comparison across many worlds, rather than fixation on any single one. It requires patience, because the timescales over which confidence builds are measured in years and decades rather than days. K2-18b helps define those timescales. Its proximity allows repeated observation. Its atmospheric thickness allows measurable signals. Its star's relative stability allows cleaner data. These qualities make it an anchor point, a reference against which future planets can be evaluated. Even if it ultimately proves lifeless, it will remain a benchmark for what can be measured and how such measurements should be interpreted. As more planets are studied, some will inevitably prove less interesting. Their atmospheres may be thin, chemically simple, or dominated by processes that are well understood. Others may surprise, revealing complexity where none was expected. It is in these surprises that progress will occur, not because they confirm life, but because they force refinement of models and assumptions. The accumulation of such cases will gradually transform the search. Instead of asking whether a given planet hosts life, scientists would increasingly ask how different classes of planets behave over time. Which environments support persistent chemical disequilibrium? Which stabilize quickly into inert states? Which fluctuate in ways that suggest ongoing energy input or regulation? Life, if present, will emerge within this comparative landscape rather than as an isolated exception. It will be inferred not from a single molecule, but from consistency across multiple indicators that persist under scrutiny. This approach may feel unsatisfying to those hoping for a definitive moment of confirmation. but it reflects the reality of working at interstellar distances. Nature rarely yields simple answers when observed indirectly. Understanding must be earned through accumulation, not declaration. The James Webb Space Telescope has made this approach unavoidable. By revealing the richness of planetary atmospheres, it has shown that the universe is neither simple nor silent. It is active, varied, and capable of producing stable complexity under a wide range of conditions. Whether that complexity routinely crosses into biology remains unknown, but the boundary between chemistry and life is now something that can be explored empirically. K2-18b stands near that boundary. It does not cross it decisively. It does not retreat from it either. It occupies a narrow region where interpretation matters as much as observation, and where caution enhances rather than diminishes significance. As future instruments refine this picture, the role of planets like K2-18b will become clearer. Some will fade into context. Others will gain prominence as patterns emerge. What will not change is the underlying method: observation, comparison, elimination of alternatives, gradual convergence. This is how science progresses when confronting questions that are both profound and difficult. It advances not by certainty, but by narrowing uncertainty, not by proclamation, but by patience. And in that process, K2-18b has already earned its place. As this process unfolds, it becomes clear that the most profound change brought about by Webb is not a single observation, but a redefinition of what it means to search for life at all. For the first time, humanity is not limited to asking abstract questions about whether life might exist elsewhere. It is now able to observe distant worlds with enough precision to test ideas, discard weak explanations, and refine stronger ones. That transition marks a psychological as well as a scientific shift. The universe is no longer an empty backdrop punctuated by speculation. It is an environment that can be studied, compared, and gradually understood. K2-18b exists at the center of this transition. Its atmosphere has forced scientists to confront the uncomfortable reality that complexity alone is not enough. Chemistry can be rich without being alive. Stability can exist without biology. And yet, biology, if present, may not announce itself in obvious ways. This tension defines the frontier of modern exoplanet science. It is not a lack of data that limits certainty, but the difficulty of interpretation when systems operate under unfamiliar conditions. The temptation to overinterpret such worlds is strong. History offers many examples where early signals were initially misunderstood, only to be corrected later as methods improved. Each correction strengthened understanding rather than weakening it. The same discipline now applies here. The atmosphere of K2-18b invites speculation, but it demands restraint. Its signals must be tested against alternative explanations repeatedly, across different models, wavelengths, and timespans. Only through that repetition does confidence begin to accumulate. What emerges from this effort is not a verdict, but a framework. Scientists are learning how to distinguish atmospheres shaped primarily by physics from those that may require sustained chemical input. They are learning which molecular combinations persist naturally and which tend to collapse unless continuously replenished. They are learning how clouds, photochemistry, and stellar radiation complicate interpretation. Each lesson reduces uncertainty, even if it does not eliminate it. This gradual reduction is how boundaries are drawn. Not sharp lines, but regions of likelihood. Over time, Some planets will drift away from the boundary as non-biological explanations prove sufficient. Others will remain near it, resisting simple categorization. It is within that resistant group that the strongest candidates for biological influence may eventually be found. K2-18b remains within this zone not because it proves anything extraordinary, but because it refuses to settle into an easy explanation. Its atmospheric chemistry is consistent, repeatable, and measurable, yet still open to interpretation. That combination makes it scientifically valuable regardless of the final outcome. As more worlds enter this category, comparison will become increasingly powerful. Similar atmospheres around unrelated stars will strengthen certain interpretations. Differences will reveal which factors matter most. Population-level analysis will replace isolated debate. In this way, the search for life will gradually resemble other branches of planetary science, where understanding emerges from patterns rather than singular cases. This evolution also reshapes public expectations, even if slowly. The idea of a sudden announcement declaring life discovered elsewhere becomes less likely. Instead, recognition may come quietly, through a convergence of evidence that leaves fewer and fewer alternatives standing. When that moment arrives, it may feel understated compared to its significance, not because it lacks importance, but because certainty will have been earned gradually rather than declared abruptly. The role of telescopes like Webb in this process cannot be overstated. They do not provide answers. They provide constraints. They allow hypotheses to be tested against reality rather than imagination. They reveal complexity where simplicity was once assumed. And they expose the limits of current understanding clearly enough to guide future inquiry. K2-18b has already served this purpose. It has influenced how future missions are planned, how instruments are calibrated, and how data is interpreted. Its atmosphere has become a reference point, a case study that shapes the questions asked of every similar world observed thereafter. As time passes, newer discoveries may draw attention away from it. Brighter signals, closer planets, or more Earth-like targets may capture the spotlight. But the methodological lessons learned here will persist. They will inform how those future worlds are evaluated and how confidently claims are framed. In the long arc of exploration, this is how progress accumulates. Not through singular revelations, but through the steady construction of reliable knowledge. Each observation narrows uncertainty. Each model refines expectation. Each comparison sharpens interpretation. K2-18b is part of that construction. It does not resolve humanity's oldest question. It reframes it. It moves the discussion from belief toward evidence, from imagination toward method. It demonstrates that the universe is not silent, but speaking in a language that requires patience to understand. As instruments improve and observations deepen, that language will become clearer. Patterns will emerge where ambiguity once dominated. Boundaries will sharpen. And eventually, the distinction between chemistry alone and chemistry shaped by life may become unmistakable. That moment has not arrived yet. But for the first time, it lies within reach. At this stage in the search, it becomes clear that what is unfolding is not merely a scientific investigation, but a recalibration of scale. Humanity has spent most of its existence interpreting the universe through a single example of life, a single planet, and a single evolutionary pathway. Every assumption about habitability, biology, and environmental stability has been filtered through that narrow lens. Webb's observations, and K2-18b in particular, have begun to loosen that constraint. They do not tell us what life elsewhere must look like. They tell us that the universe is under no obligation to resemble our expectations. This realization carries weight precisely because it is uncomfortable. It forces a confrontation with the limits of analogy. Earth remains the only confirmed inhabited world, but it is no longer sufficient as a universal template. The chemistry observed on K218b suggests pathways that do not map cleanly onto terrestrial biology, yet they remain coherent, persistent, and energetically plausible. Whether those pathways include life is unresolved, but their existence alone expands the space of what must now be considered possible. What Webb has exposed is a universe that is chemically expressive. Planets are not passive recipients of stellar radiation. They are active systems capable of maintaining internal balance, redistributing energy, and sustaining complex atmospheric states over immense periods of time. Some of those states may be lifeless. Others may hover at the threshold where biology could emerge, persist, or fade. Distinguishing between these scenarios is now the central challenge. K218b illustrates how narrow that threshold may be. Small changes in atmospheric composition, stellar behavior, or internal heat flow could push a planet toward equilibrium or sustain long-term imbalance. From Earth, these differences appear subtle. From the planet itself, they may be decisive. Webb can glimpse these distinctions, but it cannot yet resolve them fully. That gap between detection and interpretation defines the present moment. As the data accumulates, one pattern is already emerging. Planets that attract sustained scientific interest tend not to be those that look familiar, but those that resist easy classification. Worlds that appear too Earth-like often turn out to be chemically simple or dynamically inactive. Worlds that appear strange, massive, or hydrogen-rich sometimes reveal the most intriguing behavior. This inversion of expectation has reshaped target selection and will continue to do so. The consequence is that the search for life is becoming less anthropocentric. Instead of asking whether a planet could host life like ours, scientists are asking whether a planet can maintain organized complexity over time. That shift may ultimately prove more important than any individual discovery. Life, if it emerges, is a consequence of sustained complexity interacting with energy and chemistry. Understanding those preconditions may matter more than identifying a specific organism. K218b is valuable because it sits within that conceptual shift. It is not being studied because it promises a dramatic answer, but because it refuses to simplify. Its atmosphere is neither chaotic nor inert. It exhibits structure, persistence, and interaction. Those qualities demand explanation, regardless of whether biology is involved. This is why the language surrounding the planet has remained careful, even as public interest has grown. Scientists understand that the cost of premature certainty is high. Once a claim is made, it shapes interpretation, funding, and expectation. Undoing it requires more evidence than making it did. The discipline applied here is therefore deliberate. It protects the integrity of the process as much as the validity of the conclusions.